Hi Bobcats! In this video we're going to take a look at properties of a solution that are different from properties of the pure solvent because of the presence of particles dissolved to make it a solution. In this video we'll look at the general ideas behind it, and then in the follow-up video we'll look at some specific examples. Our objectives are to perform calculations on these properties, which are called colligative properties, and we want to be able to handle colligative properties whether we're talking about a non-electrolyte solute or a solute that's an electrolyte. Colligative properties depend on the concentration of your solution, not on what the particles actually are. And so we are going to be very interested in how many particles we get out of our solute as it dissolves. The four colligative properties we're going to discuss are freezing point depression, boiling point elevation, vapor pressure lowering, and osmotic pressure. So let's start with vapor pressure lowering. That is the diagram down here at the bottom. We have a volatile solvent. Volatile means a liquid that readily evaporates. And so we have a liquid here that in a sealed container will evaporate, and some of that vapor will be trapped inside of the container. It exerts what we call the equilibrium vapor pressure for that solvent. Well, if we introduce solute particles to the solvent and make a solution, the solute particles interfere with the way the solvent particles interact with one another, and they make it more difficult for the solvent to evaporate and exert vapor pressure. So we say that the vapor pressure of the solution is lowered compared to the vapor pressure of the pure solvent. Over here on the right, we have a diagram illustrating osmotic pressure. Osmosis is the flow of solvent particles through a semi-permeable membrane. Semi-permeable membrane simply means that some particles can flow through it and some can't. Typically the solvent particles are tiny, the solute particles are big, and so it's the solvent that can flow through the membrane. Osmotic pressure refers to the pressure that is exerted because of a concentration difference between the pure solvent and the solution. This is all we're going to say about vapor pressure lowering and osmotic pressure. I would expect you to be able to answer a question on vapor pressure lowering, recognizing that the vapor pressure of the solution is lower than the vapor pressure of the pure solvent. The ones that we're going to spend a lot of time on here are freezing point depression and boiling point elevation. So we'll start tackling that on the next slide. Freezing point depression happens because when a solute is added to a pure solvent, the solute particles interfere with how that solvent crystallizes. So the top diagram shows a pure liquid, and it's in the liquid state. If we remove energy from it so that it can freeze, it forms a solid where the particles are lined up very neatly in a crystal structure. Well, if instead we have a solution, so those little yellow solute particles are mixed up in there, it becomes much harder for the solvent particles to arrange themselves in that crystal structure because the solute particles get in the way, interfere with those intermolecular forces that are binding the solid particles to one another. And so we have to remove even more energy for the particles to be able to turn into a solid. The equation that goes with this says that the change in temperature, right, so delta T sub F means the change in the temperature at which this will freeze is equal to the freezing point of the pure solvent. So for instance, if we were talking about an aqueous solution, T sub F of the solvent would be 0 degrees C. And then we're going to subtract from that the freezing point of the solution. The solution is going to freeze at a lower temperature. So if it was water, it'll freeze below 0 degrees C. this is the reason that in wintertime, when roads are expected to become icy, the city will put down salt solutions. The salt particles will interfere with the water molecules, and they will keep the water liquid to a colder temperature and prevent the streets from icing over. So this top line is just defining what this delta T sub F is. The bottom line is giving us a way to calculate how much the freezing point will be lowered. So we could also say down here on the left-hand side, delta T sub F is equal to I times K sub F times M. I is something called the Van't Hoff I factor, which we'll look at on the next slide. K sub F is a constant that depends on the solvent. It doesn't matter what the solute is, but if it's an aqueous solution, we go and we look up the number for K sub F for water. And then the lowercase m is going to be the molality of the solution. All right, let's take a look at that I factor. The Van't Hoff I factor is going to tell us how many moles of particles we get for every 1 mole of the solute that dissolved. Now, in order to accurately predict this, we need to remember a couple of things from Gen Chem 1. First of all, a molecular or covalent compound is made up of a nonmetal bonded to another nonmetal, and sometimes we'll end up with even more than just 2 different elements in there. When a molecular or covalent compound dissolves in a solvent, it dissolves as a complete molecule. So for every 1 mole of your solute, you get 1 mole of particles in solution. This is what we refer to as a non-electrolyte. The particles that dissolve, those molecules, have no charges associated with them, and because it's a non-electrolyte and we get 1 particle for every 1 molecule that dissolves, this has a Van't Hoff I factor of 1. It's real critical as you're reading the problems. If the word non-electrolyte appears to describe the solute, they're trying to say I equals 1 for your calculation. Now, the other type of compound we're going to be concerned with will be ionic compounds. They are made up of a metal plus a nonmetal, or in place of one or maybe even both, you'll see a polyatomic ion, like the nitrate ion, the sulfate ion, the acetate ion. And when an ionic compound dissolves, we're going to get multiple ions. We'll get at least 2 ions, 1 cation and 1 anion. We may get even significantly more than that. And so the I that you get from ionic compounds will be greater than or equal to 2. The smallest it'll be is 2, but it can easily be bigger than that. Here's an example. Oops, I kind of wrote over my diagram here a little bit. Here's an example of something like the very last one that I have in this list, AlCl3. Aluminum is a metal that when it forms compounds has a charge of +3. So this blue ion might be our aluminum +3 ion. And then chloride forms ions that have a charge of -1. So each of these purple ones might be a Cl -1. And when aluminum chloride dissolves, we have for every 1 mole of aluminum chloride, we're going to have 4 moles of particles. 1 of those is aluminum and 3 of them are chloride. So in this case, let me go ahead and just fill in this equation. AlCl3 solid dissolves. We're going to get an Al +3 plus 3 chlorides, and that's going to mean that our I factor is equal to 4. 3 chlorides plus 1 aluminum gives us 4. let's just work these backwards. Barium chloride dissolving. Well, barium is an alkaline earth, so that means it dissolves with a charge of +2. And then each one of those chloride ions is a -1. So we're going to get 2 chlorides to balance the +2 charge on the 1 barium. So 1 barium plus 2 chlorides gives us an I factor of 3. For sodium chloride, when it dissolves, we're going to get a sodium +1 ion and a chloride -1 ion. So 1 sodium plus 1 chloride gives us an I of 2. And then we have glucose, C6H12O6. Well, this one is molecular or covalent. It's all nonmetals. And so when this one dissolves, we only get one particle. We get C6H12O6. It all sticks together as a single molecule when it dissolves up in water. It is a non-electrolyte. None of these this glucose particle does not have a charge, and so we have an I factor of 1. The other new symbol in our equation for freezing point depression was the K sub F. This is known as the freezing point depression constant, and when you go to a table and look it up, you want to look for a solvent, not for the solute. So if we're dealing with an aqueous solution, we would want to look up the numbers for water. This particular table I pulled out of Sapling Learning's Chempendix. The link for Sapling Learning's Chempendix is given here. So if you're working a problem with water and we're looking for the freezing point depression, the K sub F value is 1.86 degrees C per molab. And this table is nice because it also tells you for these different solvents what their normal freezing point is. So pure water freezes at 0 degrees C. If instead we were looking at boiling point elevation, which we will do shortly, the KB value would be 0.512, and the normal boiling point for pure water would be 100 degrees. So I like this table because we're often messing around with not just the delta T sub F, but trying to calculate what the actual new freezing point would be. And so it's nice to have for reference what the original pure solvent freezing point is. So in this section, we are looking at colligative properties, which are properties that depend on the concentrations of our dissolved particles. And we had vapor pressure lowering. You do need to know that vapor pressure decreases as solute particles are dissolved. And we looked in general at freezing point depression. We'll see that there's an almost identical process for boiling point elevation in the next video, but for freezing point depression, we have that delta T sub F is given by the Van Hoff I factor times the freezing point depression constant times the molality of the solution. And remember that delta T sub F, that's the change in the freezing point. So that really means that is, whoops, I do not need the delta right there. Let me get rid of that delta. We are looking at the freezing point of the pure solvent minus the freezing point of the solution once the solute has been added to it.